from first principles when it pops up. So we have some learning intentions and success criteria there, but we want to understand how the derivative is defined and calculated using first principles. Now, in order to do this, we need to look at our gradient of a secant. We looked at secants yesterday and finding the gradient of them yesterday by finding our average rate of change. So we're going to investigate that a little bit deeper this morning. So the line passing through the 2 points x1, x2 on the graph of a function is called a secant. So we find the gradient of the secant by using the formula m equals our y2 minus y1 over our x2 minus x1. Our gradient of the secant gives us our average rate of change between the 2 points. We calculate an approximated value for the gradient of the tangent at a point on a curve by taking another point close by, then calculating the gradient of the secant joining these 2 points. So this is pretty much just going over what we did yesterday. So for our function, which is x cubed, we want to find the gradient of the secant PQ, where P is the point where x equals 2 and Q is another point on the curve where x equals 2.1. We then want to choose points for Q closer to P, and these results will help us to estimate the derivative, so f dash of 2, and we want to, which is the gradient of the tangent at the curve P. So what we are going to be doing for this first one is we have to find out, we have our first point is P, and P is the point 2f of 2. Now, this is where to find out what f of 2 is, so to get f of 2, it is equal to 2 cubed by substituting it into our function, which is equal to 8. So therefore, P is going to be the point 2,8. Okay, and then what we want to do is, when we are doing this, we want to find out, so we can find out all of our points, so we can look at Q and find out what Q is as well, or we can do it a little bit different. So what we want to do is we want to find the gradient of PQ. And so what we do with our gradient of PQ is we have the point P, which is 2f2, and then our point Q is 2.1 f of 2.1. So what we can do is when we're finding the gradient of our tangent, it's y2 minus y1 over x2 minus x1. So technically we'll have our our y2 is f of 2.1 minus our f of 2 over our 2.1 minus 2. So this is just using our function notation. And so what we have here is it is equal to, well, our function is x cubed, so it will be 2.1 cubed minus our 2 cubed all over 2.1 minus 2, which that is just, can be put straight into our calculator to get 12.61. So that means our gradient of PQ is 12.61. What we now want to do is we want to pick other points that are close to it. So we might pick the other side of point 2. So we have 2 and 2.1. So now we might do 2 and 1.9. So if we do, let's pick another letter. Let R be the point 1.9 f of 1.9. What we will have is the gradient of PR or RP, it doesn't matter, is going to be f of 2 minus f of 1.9 over 2 minus 1.9. So then that will equal 2 cubed minus 1.9 cubed all over our 2 minus 1.9. So that works out our gradient of PR or RP, doesn't matter with the order of the letters. That works out to be 11.41. Okay. So what we can see, and we can do more and more of these, but the more and more that we do and the closer that we get to 2, we can see that as x approaches 2, our gradient f dash of 2, or our derivative function, it approaches what number? What whole number is it going to approach? What number is in between the 2 gradients that we found? 12. So it's going to approach 12. Okay, so what this means is if we were to differentiate, which I'll teach you how to do on Friday, our function, x cubed, and then substitute it in 2, the answer should be 12. Okay, turn the page for me once you've copied that down. And what we're going to be looking at now is our difference quotient. So our difference quotient is our gradient of our tangent, and we measure the instantaneous rate of change of any point on the graph of a function by using limits to find the gradient of the tangent at the curve at that exact point. So this is called differentiation from first principles. And using this method, we can find a general formula for the derivative function y equals f dash x. So we want to find the instantaneous rate of change or gradient to the tangent to a curve y equals f of x at a point p of x of f of x. So this point here is our p of x of f of x. It's our point. And what we want to do is we want to draw a tangent. So a tangent is a straight line at that point, which tells us what our gradient is. So what we need to do for this is we want to choose a second point. And so we've picked a second point Q, which is close to P with coordinates Q is x plus h, f of x plus h. Okay, so that's our point Q up there. So we've added h to our x value and then we've substituted it in. Now just remember this orange line here between our 2 points is our secant. And so what we would do if we were going to find our average rate of change, we would find our gradient of our secant. But we can use what we have with these 2 points to find our gradient of our secant. Using our formula m equals y2 minus y1 over x2 minus x1 to get our 2 points. And that will tell us what our gradient of our secant is. And then we're going to introduce limits to get the exact point. So we have that m equals y2 minus y1 over x2 minus x1. We have our point x fx, and we have our point q x plus h f of x plus h. And this is where we have x1, y1, I got that correct this time, x2, y2. So if we wanted to find our gradient, it is going to equal our y2, which is our f of x plus h, minus our y2, which is y1, which is f of x, all over our x2, which is x plus h, minus our x1, which is just x. Now we can tidy this up a little bit. So what we will get is nothing tidies up with our numerator. We'll just get f of x plus h minus f of x. But on our denominator, what is x plus h minus x? It's just h. Okay, so our gradient, or our gradient of these 2 points where we don't know what we've plussed on, to find our other point to get our h, okay, this is called the difference quotient, and it gives us an average rate of change. Now, to find the gradient of the tangent at P, we make h smaller as shown. So see in this diagram here, as they make the point Q, we get closer and closer and closer. So we're making that distance from our x coordinate to that other x coordinate of h a lot smaller. And so what we have is our h value starts to approach 0. Okay, that's what our arrow means. So h approaches 0. What we get is that our gradient of our tangent becomes and gets involved with this thing called a limit where h approaches 0. Now, A limit is just putting a, what's the right word? It's putting like something into it. So we're just going to say that we're going to eventually let h equal 0 because we don't want any distance between that point. We pretty much want point Q right on top of point P. So what we do is the gradient of the tangent becomes this formula, the limit as h approaches 0 of fx plus h minus our fx all over h. And we call this our f dash x, or our dy on dx, or our y dash. And this is our formula for differentiation from first principles, which is that f dash x is equal to our limit of f of x plus h minus f of x all over h. Now, unfortunately, this is one of the formulas that isn't on your reference sheet. So it is a formula that you have to remember yourself. Sometimes in past HSC questions, they've given that to you. Otherwise, you need to remember it. So it's something that you want to have stored to your memory bank, that formula. And when you get straight into your exam and can pick up your pen, I'd be writing it down on your reference sheet, because you can always add formulas to your reference sheet once you get into an exam. So what we have is our different differentiation notation. Like I said yesterday, we had two different mathematicians discovering calculus at the same time. One was Isaac Newton, and he wrote the derivative of f of x as f dash x, but there are other notations, such as Leibniz wrote the derivative as dy over dx, which comes from delta y over delta x, which means the change in y with respect to the change in x. So it means the derivative of y with respect to x, or the difference in y per the difference in x. Some other notations that we have are y dash, or d on dx of y, d of dx on f of x. So we'll see all the different notations, but for today, we're going to be using our f dash of x for our questions. So go to the next page for me, because we're going to go through our first example. I'm going to step it out how we do this very deliberately. So the question asks us to differentiate from first principles to find the gradient of the tangent to the curve y equals x squared plus 3 at the point where x equals 1. So the first thing we want to write down is our differentiation from first principles formula, which is our f dash x is equal to the limit as h approaches 0 of f of x plus h minus our f of x all over our h. Now, a great thing that's going to happen is when you do this exercise, you're not just going to jump to a question that looks like this straight away. You're going to jump to a question where it gets you to step it out a little bit more. So the first thing that we need to think and see is what is our f of x. So in our question, we are told what our function is. We're told that our y equals x squared plus 3. That is our f of x. So we're told that our f of x is equal to x squared plus 3. So we already have that part that we're going to be substituting into our formula. The next part that we need to find is our f of x plus h. Now, with our f of x plus h, it is using our function notation, and instead of where we have an x, we're going to replace this with an x plus h. So what this will look like is in our function we have x squared plus 3, so we will have x plus h all squared plus 3. So all I have done is where we had an x in our original function, we've replaced it with an x plus h all squared. Now, what we need to do is we need to expand this out. I'm hoping some of you noticed that this is an example of a perfect square. So some of us will be able to expand it straight away into a perfect square, because we have a plus b all squared is a squared plus 2ab plus b squared. That's going to save you time if you can use that. If you can't, that is totally okay. So if you can expand it, you will go straight to that f of x plus h is x squared plus 2xh plus h squared plus the 3 at the end. Now, if that expansion and you're not sure how that's all happened, we have two brackets. So our x plus h all squared is just x plus h times x plus h with our plus 3 on the end. So if we expand those brackets, it's x times x, which is x squared, x times h plus x times h, or h times x, plus h squared plus our 3. And then we just collect our like terms. Does that make sense? Yeah? Okay, so now that we have what our f of x plus h is expanded, and our f of x equals x squared plus h, what we want to find is we can find out what f of x plus h minus f of x is equal to before we substitute it into our fraction. So we know that f of x plus h, we have found that to be x squared plus 2xh plus h squared plus 3 minus, now I'm going to make sure I put my f of x in brackets because that minus is going to affect my x squared and my plus 3, meaning that this will equal x squared plus 2xh plus h squared plus 3 minus x squared minus 3. All right, so remember that when you are minusing a term or something like f of x, you need to put it in brackets because that negative affects every term inside that bracket or inside that function. From here, we can hopefully collect like terms. So we should see that x squared minus x squared goes away. And we also should see that plus 3 and minus 3 cancel out, leaving us with 2xh plus h squared. Okay, that is what our f of x plus h minus our f of x is equal to. So now what we're going to do is we can take this one step further because what do both terms have in common? H. So we can factorize out. So we will have that this is equal to h lots of 2x plus h. Okay, now what we're going to do is we're going to put that into our formula up the top. So we might even just write our formula down one more time. So f dash x equals our limit as h approaches 0 of our f of x plus h minus our f of x all over h. So what we will be doing is we'll be substituting in our f of x plus h minus our f of x onto our numerator there. So we will have f dash x equals our limit as h approaches 0 of h over 2x, h lots of 2x plus h all over h. Now, what do we notice about this fraction? We can cancel out the h's, so that is what we are going to do. Now, something that we need to remember is we can only cancel out the h's when they're factorised out. Okay, you can't cancel unless it's factorised. So what we'll have is that f dash x is equal to the limit where h approaches 0 of 2x plus h. Now, how we get rid of our limit and to find what the derivative is we sub in h equals 0 to cancel out the limit. So what that means is we'll get f dash x is equal to, so the limit goes away because we're substituting in a 0 for our h, so it will be 2x plus our 0. So that means we'll have f dash x is equal to 2x. So what we have found so far is that the derivative of our original function, which our original function was x squared plus 3, the derivative is just equal to 2x. Now, we haven't quite answered the question because it asked us to find the gradient of the tangent at the point where x equals 1. So now we just need to sub in x equals 1. So f dash of 1 is equal to 2 lots of 1, which is equal to 2. So therefore, the gradient of the tangent is 2 at x equals 1 for y equals x squared plus 3. Okay, this is a brand new concept, so I expect us to struggle with it a little bit. We're going to do one more example. If you want to go ahead and try and do the next example by yourself, you're more than welcome to, but I will be starting to go through it in 20 seconds. So turn over the page for me. All right, so the first thing that we want to do is we want to write down our differentiation from first principles formula. So f dash x equals our limit as h approaches 0 of f of x plus h minus f of x all over h. Now, in our question, we will always be given f of x. So f of x is equal to our 2x squared plus 7x minus 3. We then want to find our f of x plus h. So where we have an x in our f of x, we're going to replace that with our x plus h. So this will be 2 lots of x plus h all squared plus 7 lots of x plus h minus 3. Now, we have a perfect square again. So our perfect square of x plus h all squared will be our x squared plus 2xh plus h squared that we can substitute in straight away. So we'll get 2 lots of x squared plus 2xh plus h squared, close the bracket, plus I'm just going to expand our 7 lots of x plus h straight away. So 7x plus 7h minus our 3. And so what we'll get is that f of x plus h is equal to 2x squared plus 4xh plus 2h squared plus 7x plus 7h minus 3. What we want to find now is we want to find out our f of x plus h minus our f of x. So to find that, we'll have our f of x plus h minus our f of x will equal our 2x squared plus 4xh plus 2h squared plus 7x plus 7h minus 3 minus in brackets our f of x, which is 2x squared plus 7x minus 3. So then this is equal to 2x squared plus 4xh plus 2h squared plus 7x plus 7h minus 3 minus 2x squared minus 7x plus 3. So where do you think people go wrong in this? In that line right there with multiplying the minus in. So if you're going to make a silly error, that's probably where you're going to make it. Okay, from here, you should be able to cancel out all your constant terms and all your terms that just have an x in it and no h's. So you should be left with terms that have h's. So our 2x squared cancels out with our minus 2x squared. Our 7x will cancel out with our minus 7x. And our minus 3 will cancel out with our plus 3. So that means that our f of x plus h minus our f of x is equal to 4xh plus 2h squared plus 7h. Okay, now we need to factorize out the h. So we'll get h lots of 4x plus 2h plus 7. And that is what our f of x plus h minus f of x is. that we are going to substitute into our formula. So we have our f dash x equals our limit as h approaches 0 of our f of x plus h minus our f of x all over our h. So replace that numerator with what we have on the line above. So we'll have that f dash x is equal to our limit as h approaches 0 of h lots of 4x plus 2h plus 7 all over h. We can then cancel those h's out. See you later. So we're left with f dash x equals our limit as h approaches 0 of 4x plus 2h plus 7. Now, to remove our limit, what we have to do is sub in h equals 0. So we'll get f dash x is equal to 4x plus 2 lots of 0 plus 7. So f dash x is equal to 4x plus 7. And this question didn't ask us to find the gradient of the tangent at a point. It just asked us to differentiate. So the derivative of what we started off with, which was our 2x squared plus 7x minus 3, is equal to 4x plus 7.